Hey guys, welcome back. This video is a short introduction to neural networks. So today I'll mainly I'm going to introduce neural networks. I'll talk about neurons, I'll talk about activation functions, and we'll talk about the construction of neural networks, and I'll finish with two time examples. So as an introduction, I would say that a neural network is a set of mathematical neurons connected and ordered into layers. The layers are usually defined as input, hidden, or output layers, and the input data is usually pushed forward into the network through the input layer. The mathematical neurons, they do transform the input using one or more activation functions, and the resulting signal is then sent to the next layers. So the output layer receives the final resulting signal and compares it to the output it tries to approximate. The definition of a neuron is defined as a cell unit that receives and sends signals. A neuron is usually dotted with what we call a set of perceptors, and the perceptors are considered as the hubs through which external signals, inputs xi, are received. The neuron is also dotted with what we call an activation function, f, which transforms the inputs. The activation functions usually assigns different weights, and they call wi's, to the inputs and sum them up. When the neuron receives enough stimuli, it may become active and fires by releasing a signal, and otherwise it would remain silent. This is usually determined by the activation function if the weighted sum of the inputs reaches a certain threshold. So I will cite a couple of activation functions. I'll talk mainly about simple ones and a little bit more complicated ones. So I'll start with what we call binary or Relu functions. So a neural network may have different activation functions. And to begin with, binary step function does not apply any transformation. It simply performs a binary classification, sending either 1 or 0. It is mainly a relic from the past, as it does not allow for stacking of layers. And if the first layer activates fully, there is no need for addition of layers. So the rectified linear unit, Relu x, which sends back the maximum between x and 0, is an activation function that gives flexibility and adaptability. It allows to move from the limited power of linear steps, and Relu is usually applied to every neuron in every internal layer. Sigmoid functions, or what we call a logistic activation function, is commonly used, which we call the sigmoid function. It writes as f of x equals 1 over 1 plus e to the power minus x. And the sigmoid function provides a steep gradient around the 0 point. An output from a previous layer may not be fully activated because it's very small. And each layer can then do its part to bring a signal to full activation. The sigmoid function produces a problem which is called vanishing gradients, in which the network refuses to learn. And this is mainly due to the fact that x needs to be truly huge to create even small changes in y. The last activation function we'll see together is what we call the hyperbolic tangent function, tan h, which is a kind of a scaled sigmoid function, which has more gradient strength. Essentially, the curve here is steeper, so decisions are made more quickly. And the usual hyperbolic tangent used is the tan h of x over 2, which writes as ex minus 1 over ex plus 1. So this figure compares the graphs of the two Relu and the tan h of x over 2 functions and their two first derivatives. The last thing we'll see before the examples are the composition or in the construction of the neural networks. The composition intends to build what we call a learning function, f of xw. And here the weights w capture the information from the training data x. The learning function usually writes as a composite function, fn of fn minus 1 till f1 of xw, where n is the number of layers in the network. For example, the input to fk is a vector xk minus 1 of length nk minus 1, and the output is a vector xk of length nk, which is ready to become the input of fk plus 1. So the function fk has two parts, a linear part and a nonlinear part, and the linear part yields akx minus 1 plus bk, and the ak here is the vector of the weights, the w the W's, and BK here is a bias that makes the linear part affine. The nonlinear part function, like Relu, is applied to each one of the linear parts, which gives back the output, xk. The chain rule, gradient descent, and backpropagation. So once we receive the approximation f of xw, we compare it to the current observed y, and we do compute what we call the error. So the chain rule is applied to the error to the square to get the current component values of the error gradient. So we compute the gradient of the error. And for example, if you are using the Relu function, these derivatives are easy, and it's derivative because the derivative is either 0 or 1. While for other activation functions, this may take more time and consume more resources. The weights values are then adjusted following gradient descent or steepest, stochastic, or even more sophisticated methods like the Newton-Raphson method. And the gradient methods were previously detailed in this course, as you know. So the best weights obtained are then fed back to the layers neurons by backpropagation. And this aims to prepare the weights to be used for the new test data. So well, let's start with a small example. In the file, a generic function neuron in Jupyter Notebook, I will post the video a little bit later. We randomly generated 2 data vectors, x1, x2, with 150 entries. And we also generated a vector of output. This way, we had y, which is equal to 3x1, 4x2, plus 2 exponential of x1 plus x2 plus 4x2 cubed plus 5. And we would like to see how the sigmoid function can be used to get the best weights from the training data, consisting the first, here for instance, 100 or 120 data entries. We then test these weights on the remaining 30 or 50 data entries. Our network is quite simple, as all neurons at the input layer apply the same weights. And the result of the optimized weights is then pushed back to be used in the next push forward. And we compare the results of the neural network to simple linear regression using the pseudo-inverse matrix. Here, what you will see later on is that the linear regression here wins by a tiny margin. And the following graph displays how the neural network root mean square error, RMSE, decreases with weights optimization. Okay. In the second example, we use a quadratic function in this file, generic function neuron 2. We used a quadratic function and the Newton-Raphson method to boost the weights optimization. And the result of the optimization of the weights is then pushed back to be used in the next push forward. And we compare the results with the previous case of a sigmoid function and the linear regression. What we find out is that the quadratic activation function here wins by a large margin because of this boost given by the Newton-Raphson method. And the following graph displays how the Newton-Raphson speeds up the weight optimization process. In fact, it took one single iteration with the Newton-Raphson method to get the optimal weights. So that's it for this short presentation. I'll continue with the details of how these were implemented. Thank you very much.